Hello friends, a very warm welcome to all of you to this power pack session of Fluid Mechanics by the GATE Academy. So in this session what we are going to do is we are going to discuss a few questions which are like repeated again and again in the GATE exam. And most of the questions that I have brought for the class, these are subjective questions, and some of these questions I sometimes discuss in the class also with the students, and we will try to cover as many aspects related to the topics through those questions. Okay, so most of them are in subjective form, but I will try to introduce the objective points in those subjective questions only. And what I believe is that now the GATE exam is very nearby, so it's only like 15 or 20 days are left. And for me, what I believe is that in the last days you should not at all focus on doing new things. Just revise, keep on revising already done work. Okay, keep on revising the subjects. For example, if you are mechanical students, then revise your production engineering 15 to 17 marks, revise maths 13 marks, revise fluid mechanics, SOM and thermodynamics. I mean the subjects which have more weightage. Okay, so revise them again and again. So from the very morning, like when you wake up, you should start revising the concepts, and even in the night while you are in the bed, you should try to memorize what I have revised today. Okay, and particularly for those students who feel that their concentration is not that strong, so what they can do is they can keep their table with the wall, facing the wall. Okay, and try to sit in the corner so that nothing else is there in your view. Okay, also try to make sure that except for your notes and your pen and copy calculator, there is nothing else on the table. Okay, otherwise what happens is you keep the laptop also on the laptop, songs are going on or movie is there, movie is running, and side by side phone is also there. You keep on checking WhatsApp and all that stuff, and all the time is wasted, all the important time is wasted. Okay, so please note that this social media and new movies and all that stuff has to be avoided. There is no need of getting general knowledge of what is happening in Bollywood now. Okay, what is more important is your BTech syllabus, your GATE syllabus. That is most important. Okay, and one more thing, that you can revise by talking also, by speaking also. Matlab, for some students, and particularly in my case also, when I was doing my BTech, or the GATE, I was preparing for GATE exam. So in my case also, I felt like my concentration was much more stronger when I would revise by speaking. I would like do like this. Acha, ab aise ho jayega. I mean, I hope you are getting the point. How to revise. Okay, so concentrate a lot on revision. Spend like at least 8 or 9 hours of revision or 10 hours of revision, and then in the night 2 to 3 hours revising what you had revised in the morning and afternoon. It has to be like this. Okay, so all the very best, and I think let's start. So let us see what the first question is, and let me discuss the first question. Okay, so what the first question says is that consider a water pipe of length 10 meters and diameter 10 centimeters. Through this pipe, the discharge increases at a rate of 1 liter per second square, and the initial discharge is 0.5 liter per second. Calculate the total acceleration of the flow. Also find out the pressure gradient in the flow and the corresponding pressure drop required to be maintained between the inlet and outlet of the pipe for the same flow. Okay, so give a reading please. So I think the question is very easy. Actually what the question says is that let us suppose there is a pipe, and the pipe has a length of 10 meters. So this is the pipe length. Let us call it as L. 10 meters, and also the diameter of the pipe D, that is equal to 10 centimeters. Now what they are saying is that the discharge, initial discharge through the pipe. So initial, I think whenever we do some analysis, initial time instant means t equal to 0. So what they are saying is that at time instant t equal to 0, the discharge is 0.5 liter per second. Okay, and then they have given a term that says the discharge increases at a rate of. Now discharge is also increasing with time, and discharge increases at a rate of 1 liter per second square. Okay, please note, what is discharge? It is liter per second. So basically what they have given you, del Q by del time, that is equal to 1 liter per second square. Okay, so discharge upon time. This is how the discharge is increasing. Now for the same condition, they are asking you to find out the acceleration in the flow, and then they are asking you to find out the pressure gradient in the flow and corresponding pressure drop. Okay. Now actually in this particular case, what we need to understand is that whenever such questions come, so what is acceleration? I think acceleration is nothing. Acceleration is simply dv by dt, right? Acceleration is simply dv by dt. So if you know the velocity as a function of time, you can get this derivative and you can predict your acceleration also. Okay. So always remember, whenever the acceleration in the flow has been asked, you simply need to find out the velocity field. You simply need to predict the velocity field, and by derivating the velocity field with respect to time, total derivative of velocity field with respect to time, you will get the acceleration. But what is velocity field? I think field is a mathematical term corresponding to Eulerian approach. So I always tell that field doesn't mean the place where you are growing carrots or vegetables. Here the field is a mathematical function. It simply means any quantity which is a function of x, y, z and time. Okay. So we need to write down the velocity field, and from the velocity field we will get the acceleration field also. But the question comes, how to find out the pressure gradient then? I think if we know the velocity values at inlet or outlet, we can find out the pressure values also using the Bernoulli's theorem. Okay, I think we can do it. But check. If we consider this pipe of uniform cross section, A1 V1 equal to A2 V2. Why? Because we are talking of water. Now area at 1, area at 2 are same. So V1 and V2 will also be same. Okay. So I think you will say that V1 and V2 are same. So using Bernoulli's equation, we can find out the pressure drop also. So what your equation will become? It will become P1 by rho G plus V1 square by 2G plus Y1 is equal to P2 by rho G plus V2 square by 2G plus Y2. Right? So V1 and V2 are equal. So this will cancel out. Since nothing has been mentioned about the pipe, vertical or horizontal, we will consider it to be horizontal only. So Y1 and Y2 will cancel out. And what you will get is, you will get P1 by rho G is equal to P2 by rho G. So you are getting the pressure at the inlet is equal to pressure at the outlet. Right? I think this is what we are getting. So actually, this problem, this Bernoulli's equation is not valid over here. This is what I feel. The Bernoulli's equation is not valid over here. Right? Why it is not valid over here? Because when we were talking of Bernoulli's equation, we derived this equation using steady state systems. I think you have derived this equation using steady state systems. So when we are talking of steady state systems, any quantity will not be a function of time. Any quantity, whether it's pressure, whether it's velocity, whether it's density, whether it's discharge, any quantity should not be a function of time. But I think here the discharge is changing with time. So when discharge is changing with time, this is not a steady state flow. This has become a condition of unsteady state flow. So your Bernoulli's equation will also be not applicable. Okay. So always remember that first of all apply Bernoulli's equation only when the flow is steady state. If the flow is unsteady state like this, you cannot apply Bernoulli's equation. Okay. So I think our first intuition, this has been like cancelled, right? We cannot use Bernoulli's equation to predict the pressure drop in this case. Okay. So the question comes, how to do it? So let's see. So actually, since I cannot use Bernoulli's equation, I will try to move through the velocity field. Okay. And once I know velocity field, so velocity field means I know acceleration. But I hope you know that whenever we know acceleration, Newton's second law of motion says net force is equal to mass into acceleration. And on any fluid element, the net force will be pressure force plus viscous force plus gravitational force. Since nothing is mentioned about viscosity of water, we will consider it to be a non-viscous fluid only. So viscous forces will be zero. Fluid is flowing horizontally, so weight will be 0. So what you get is net pressure force is equal to mass into acceleration. So from acceleration, you can predict the pressure force, that is the pressure gradient and the drop also. Okay. So always remember, in such cases, once we know the acceleration through the velocity field, finding out pressure gradient also becomes easy. And I think this is what we have done in the derivations of flow through pipes and flow between parallel plates, or while writing down Euler's equation and then going on to Bernoulli's equation. Everywhere we do the same. So what I told is, from fluid kinematics we get the velocity field using some experiments. We derivate the velocity field, we get the acceleration, we put this acceleration into Newton's second law of motion and predict everything that is required, say for example pressure gradient. So let's first of all solve the first part, that is acceleration field. So the question comes, how to predict the velocity field? Now actually in our syllabus, for such type of questions, there are two inherent assumptions are there, which are generally not mentioned in the question. Okay, so I will ask you to cram this. Whenever such questions have been asked where they are asking you acceleration in the flow, you have to cram two assumptions. And what are those two assumptions? Those assumptions are that if the flow passage is converging or diverging, suppose the flow passage is converging or diverging, here it has a cross section, uniform cross section, but suppose a question comes where there is a converging or diverging passage. So in that case, you will assume that the convergence or divergence is gradual. Convergence or divergence is gradual. Let's see what that means. So suppose we talk of a flow passage. This is your flow passage, okay, and this is the center line of the flow passage, okay. Let's see what is the meaning of this assumption and what will happen. Why we want to take this assumption. So what I am doing is, I am marking a coordinate system here along the center line of the flow passage, and this will be my XYZ coordinate system, okay. Now it is definitely by intuition, if I take any location over here, then I think whatever particle comes at that location, it will have a resultant velocity vector like this, isn't it? It will have a velocity vector like this. Now these velocity vectors, they will have two components. So this will be your along the y and this will be along your u, right? Now check. Suppose this angle is theta. This angle is theta, which is like half the cone angle, okay? Half the cone angle. So I think by alternate interior angles, this angle will also be theta. So what I can say is that the magnitude of y component of velocity is equal to v sine theta, right? I think using the trigonometry, basic trigonometry, okay? Using basic trigonometry. Now check. If this theta is very small, then sine theta will be negligible. And then in that case, your y component of velocity, that is v, that will also be negligible, okay. So generally what happens is, whenever we talk of flow, because of the changing cross sections, the flow will have multi-directional components, okay. There will be x component also, y component also, z component also. But what we can do is, if the theta, that is the cone angle of divergence or convergence, is very small, we can simply neglect the transverse components. So if this is the flow direction, x is the flow direction, then y and z will be the transverse directions. So you can neglect v and w, okay. So what you are left with, that if I take any cross section, which is at a distance x from the inlet, then at all the points of the section, there will only be one component of velocity, that is u. Now I hope all of you are aware of viscosity, and we know that because of viscosity, there is a formation of boundary layer in the flow. What is the meaning of boundary layer? That is the layer of the fluid which are adjacent to the solid surface. Those layers stick to the solid surface, no slip condition. And the layers of the fluid which are away from the solid surface, they have maximum relative velocity with respect to surface. So definitely at these locations, the flow velocity u will be having a value 0. And at this location, which is at farthest distance from the surface, the flow velocity will be maximum. So what I am trying to say is that at a cross section, the velocity profile is not uniform, right? But what we will assume is that in these questions, we will assume that the fluid is non-viscous in nature. So if the fluid will be non-viscous in nature, there will not be any formation of boundary layer. And since there is no formation of boundary layer, at any section, the flow velocity will be uniform. So basically, at any section, the flow velocity will appear like this, okay? And when the flow velocity at a section is uniform, then the same flow velocity is actually equal to mean flow velocity also. So how do you write down mean flow velocity? The mean flow velocity is simply discharge per unit area, okay? Okay, so please note, actual flow and mean flow velocity, they are two different terms. You can say that mean flow velocity is simply a scalar quantity which represents the discharge crossing a section. But actual flow velocity is the actual flow, that is u, v, w, and u as a variable quantity along y and z. It's like this, okay? But because of these two assumptions, we can represent the actual flow by the mean flow velocity. So whenever a question like this comes, you simply need to write down the mean flow velocity, which is equal to discharge per unit area, okay? So I think that's all. That's sufficient for the discussion of the question. So what you have to remember is that these two assumptions will be valid over there even if they are not written. So you will simply write down mean flow velocity is equal to discharge per unit area. What is this? This simply means that if in the flow I take a section, which is at a distance x from the inlet section, then at a particular time instant t, the mean flow velocity here v will be equal to discharge crossing the section per unit area of the section. Okay, this will be the mean flow velocity. Now let's write down the variables on which this mean flow velocity depends. I hope you remember that in Eulerian approach, we write down the quantities as function of location and time. Here also the quantities are function of location and time, that is x and time. Now as we are talking of mean flow velocity, that is the discharge crossing a section, and section is represented by YZ plane. So basically now our location will be represented by x only, okay? So check. I think when we talk of area of cross section, so in this particular case, the area at x equal to 0, area at any intermediate x, and area at the outlet of the section, that is the same. But if this is a converging passage or it is a diverging passage, then for different x, areas will be different. So in that case, what will happen is that area will be a function of x. Also, sometimes we have flexible passages like your blood vessels. So when fluid flows through these flexible passages, because of fluctuation in the local blood pressure, the diameter at a location keeps on changing. So area keeps on changing. So area becomes a function of time also, okay? But since you are going to talk only of rigid passages, only. For rigid passages, that is fixed solid boundaries, your area will not be a function of time. Okay? So you can simply write down area is a function of x only. Okay? So what we have is, for us, area will only be a function of x. Okay? Now similarly, if I talk of discharge, the discharge can be a function of location and time also. Now why the discharge is a function of time? So suppose initially the valve was only half open. So from the outlet we are getting a discharge of 0.5 liter per second. But now the discharge is fully open. So we are getting a discharge of 1 liter per second from the outlet. So check. Same location, outlet, initially discharge was 0.5 liter per second, but later on the discharge was 1 liter per second. So discharge has changed. Why? Because there were some changes at the beginning of the flow passage. Similarly, this is a river and here we have the glacier ice. So in winters, the rate of melting of glacier is less. So here the discharge will also be less. In the months of March and April, the rate of melting of ice is more. So here the discharge will also be more. So we are comparing two different times, January and April. So discharge can be a function of time also. What about discharge as a function of X? Now particularly here we are talking of water. So whenever you are talking of incompressible liquids, discharge is never a function of X. Why? Because incompressible fluids means like eggs. So this is an egg tray which is already filled with 50 eggs. You want to put 2 eggs from the inlet. So you will have to move 2 eggs here and you will have to move 2 eggs here. Okay. So 2 eggs at the inlet, 2 eggs crossing the intermediate section and 2 eggs crossing the outlet section. So in this particular case for incompressible fluids, discharge for all the flow sections is same. Okay. So what you can say is, you can simply say for incompressible fluids, your discharge is simply a function of time, because incompressible fluids means if 1 liter is coming inside from here, then another 1 liter will have to cross this intermediate section and another 1 liter will have to cross the outlet. Okay. So always remember, whenever you get a question like this, particularly talking of water or liquid, your area will only be a function of X, discharge will only be a function of time, and then you will write down velocity, which is discharge per unit area. This means discharge is a function of time, area is a function of X. Therefore, your mean flow velocity is also a function of X and time, right? So this is your mean flow velocity as a function of X and time. Now we want the acceleration in the flow. Okay. So when you want the acceleration in the flow, you simply need to take total derivative of velocity. So let's take the total derivative of velocity. But I hope you remember partial calculus. And in this particular case, we are taking derivative of V, which is a function of 2 variables. So when you will take the total derivative dV by dt, that is the acceleration in the flow, that will become V is a function of X. Therefore, you will have del V by del X dx by dt plus del V by del time dV by dt, dt by dt. But this dt by dt, definitely it will cancel out. So it's only this del V by del time. Now what I feel is dx by dt, that is rate of change of x coordinate, is basically the actual velocity. But actual velocity is equal to mean flow velocity. So here you will have v only. So this will become v del v by del x is equal plus del v by del time. So this is the total acceleration in the flow. Okay. Now check. I think in the acceleration, the space gradient terms, the terms which have space gradients, those represent convective acceleration, and the term which represents time rate, that represents local acceleration. What is the meaning of local acceleration? Local acceleration means, local changes means that at a particular location, say for outlet, the velocity in the morning is different than velocity in the evening. Okay. So basically in the morning, Ram was crossing this location, but he had a speed of 1 meter per second. And in the evening, Shyam was crossing this location, but he had a speed of 2 meter per second. So we are talking of different times, but different locations. So definitely we are talking of different particles also. Okay. Okay. So we are simply saying that the quantities or the conditions at a particular location change with the time. That is a local change. But what about convective acceleration? Convective acceleration simply means that when a particular particle, okay, convective acceleration means when a particular particle, when you talk of local change, you compare different particles but same location. But when you talk of convective acceleration, you talk of a single particle. So what you will say is, when this particle which is coming at inlet and it will go to the outlet, it will change its velocity. Why? Because the geometry of the flow at inlet is different than geometry of the flow at outlet. Okay. So convective acceleration means the fluid, the acceleration which a particle undergoes as it moves from one location to the other due to changes in geometry of the flow, changes in geometry of the flow passage. Okay. Whereas local acceleration means the local changes that occur at a location because of changes in discharge, because of changes in pressure and so on. Okay. So let's see. So if I will put the expression of mean flow velocity, that is discharge per unit area. So we will say acceleration is equal to discharge per unit area. Therefore, del by del x of discharge upon area plus del by del time of discharge upon area. Now, what I feel is that in this derivative, partial derivative, we have del by del x. So with respect to x, so when you are doing partial derivative with respect to x, time will be constant. Therefore, the terms of time, the functions of time, they will come out of the integral. Now discharge is a function of time, so it will come out of the integral, and area is a function of x, so it will remain here only. So you will have q square upon a into del by del x of 1 by a. And then you have del by del time. So function of x will be a constant. Therefore, a will come out of the integral. So you will have del q by del time. Okay. So for acceleration of such problems, you can also remember this expression directly. Okay. Now we have to solve the same. This is the acceleration. This is the what you say expression for the acceleration. Okay. And here we will write down discharge as a function of time, area as a function of x. You solve this, you get the value of acceleration. This portion is convective acceleration, this portion is local acceleration. See, local acceleration comes into picture when del q by del t is non-zero, that is discharge changes with the time. And convective acceleration comes into picture when area is a function of x. So if the area is a function of x, that means the area at inlet is different than area at outlet. So the flow passage is non-uniform in cross-section, converging or diverging passage. Now in this particular case, since area everywhere is same, so I think area will not be a function of x. So for this particular case, this derivative will be 0. Hence the convective acceleration in the flow is 0. So this means there is only one acceleration in the flow, that is the local acceleration. So let us write down the final value of local acceleration and our first step will be complete. So if I write down the local acceleration, that is 1 by area of the flow passage into del q by del time, I think area of flow passage can be written because this is a pipe, so area of flow passage will be pi d square by 4. So here you will write 1 by pi d square. So diameter of the pipe, that is 10 centimeters. So 0.1 10 centimeter I am writing in meters because I want answer in meter per second square. So 0.1 square and a 4 will go up. And then I have del q by del time. Now rate of change of discharge with respect to time is already given to us. That is 1 liter per second square. So here I will write 1 liter per second square. But I think in meter cube, 1 liter means 1 by 1000 meter cube. Okay, so this will be your final answer. Okay, now let's check what is the final answer. So I think this will become 1 by 100, which will go upstairs, and that 1000 will come down. So you will have pi by 1000 as well. So when I will substitute it, I will have 400 divided by 0.4 divided by pi. So the answer is 0.127 meter per second square. So this is the local acceleration in the flow. So I hope everyone has got it, understood it. Time is not much, even though I'm taking more time while solving a question, because so that I can cover as much concepts as possible. Now suppose there was a question in which area was a function of x. Then what you have to do is, first of all, you have to find out area as a function of x. You need to write down area as an expression of x. That area is an expression of x. You will substitute in the expression of acceleration and you will get your convective acceleration also. Now many times what happens is that area is a linear function of x or area is a parabolic function of x. So correspondingly in convective acceleration also there will be a term x. This means convective acceleration is a function of x. So at x equal to 0, that is inlet, and at x equal to L, that is outlet, the magnitude of convective acceleration might be different. Okay. So in the question they will mention you find out convective acceleration at x equal to 0, inlet. Find out convective acceleration at the middle of the flow passage, that is x equal to L by 2. Now check. Now let us move on to the second part. So in the second part they are asking us to calculate the pressure gradient. So I think to find out the pressure gradient, that is the pressure force, we need to move on to the Newton's second law of motion. Okay, so let us assume that here we have a fluid element, okay, which has some mass, and obviously this element has some acceleration in the x direction. Okay, now I think in the classes what we have done is, first of all, we find out the pressure distribution on all the surfaces of the element. We write down the viscous force, we write down the gravitational force, and so on, right? So summation of all the forces should be equal to mass into acceleration. This is how we write down. But for these questions, we are treating the fluid to be non-viscous in nature, so your viscous force will be 0. We have considered the pipe to be horizontal, flow is along the horizontal, so your weight component will be 0. So only pressure forces that we have to consider is along the x, and correspondingly this is ME&CE, where AX we have already found out. Okay, it is 0.127 meter per second square. Now FPX, so when you write down these values in this equation in terms of per unit mass, I hope you remember when we write down this equation in terms of per unit mass of the element, we get something like this. Minus 1 by rho del P by del X is equal to AX. This is nothing but Euler's equation, right? And in order to derive Bernoulli's equation, then I will substitute the condition that the flow is steady. So here you will be left with only convective acceleration. But this is a general Newton's second law of motion for a non-viscous fluid. In this equation, I have neither put the assumption of steady state flow, I have neither put the assumption of incompressible flow. This equation can be written for both compressible, incompressible flow, for both steady, unsteady state flow. Now in our particular case, the acceleration is only local acceleration and the fluid is incompressible in nature. So when I calculate the pressure gradient is simply minus rho into our local acceleration. So this will be, since we are talking of water, so density is water and our acceleration is 0.127 meter per second square. So ultimately we will get 1 minus 127 Pascal per meter. I think this is what we will get. I hope we have done a correct calculation for acceleration. If there is any mistake, please do check. Okay, I'm not checking it now. I'm just focusing more on method and shortcuts rather than on final numerical answers. Okay. So we have got pressure gradient minus 127 Pascal per meter. Now someone will say why the pressure gradient is negative. Now please check. The fluid is accelerating in this direction, right? The local acceleration was a positive term. This means it was along the x direction. So the fluid is accelerating in this direction. Now this acceleration is only possible if here the pressure is higher and here the pressure is lower. Okay. Now this acceleration will not be observed in a time instant but in a time period. And you can forget this last statement of mine. You need not concentrate on it. Okay. So here the pressure should be higher and here the pressure should be lower. Now how do you write down pressure gradient? I think you write pressure gradient as P at x equal to L minus P at x equal to 0 divided by x equal to L minus x equal to 0. I think this is how you write down pressure gradient. Now pressure at inlet is higher than pressure at outlet. So the smaller value minus larger value, that will be a negative only. Okay. So your pressure gradient is minus 127 Pascal per meter. Now I think using this expression we can find out the pressure drop also. So this is pressure at outlet minus pressure at inlet divided by L. Now this is equal to minus 127 Pascal. So your pressure drop, which is Pi minus Po, it is simply equal to L is 10 meters. So this answer becomes 1 to 70 Pascals. So across the pipe we have created a pressure difference of 1 to 70 Pascals. Okay. So I think in the question we have solved all the terms, that is local acceleration, convective acceleration. We saw how to write down local and convective acceleration. Then we predicted the acceleration for this particular question, and from the acceleration we found out the pressure gradient, and from pressure gradient we found out the pressure drop. Okay. Now please note, whenever the flow is steady, the pressure drop can be found out using Bernoulli's equation. Okay. But this was a case of non-steady flow. That's why I have used this particular method. Okay. Now let's move on to the second question also, and I think the next two questions, they are based on hydrostatics. So a lot of questions from hydrostatics are asked, and this particular question which we have done till now is not only asked again and again in GATE, but it is also asked in IES, ISRO, BARC and other examinations, okay? However, there might be a variation. In our question, we have discussed local acceleration. In their question, there might be convective acceleration, okay? So you need not get confused. The idea is very simple. Simply write down the main flow velocity, which is discharge per unit area, find out the expression for acceleration and then substitute the given values. Now let's move on to the second question as well. So what we have is, in the question, it's given to us, what it says is that fuel gauge for a gasoline tank in a car. So basically, civil guys, do not worry about the question. I mean, it's not going to involve any concepts of mechanical. Such type of questions are asked in civil only. In fact, more questions on hydrostatics are asked in civil rather than in mechanical. So what we have is the fuel gauge for a gasoline tank in a car reads proportional to the pressure gauge at the bottom of the tank. Okay. The tank is 25 centimeter deep and accidentally contains 1.5 centimeter of water in addition to gasoline. Estimate the height of air column in the tank when the fuel gauge erroneously reads full. And there is some figure also given to us. In the figure, the gasoline tank has been shown. The height of the gasoline tank is 25 centimeter. In the gasoline tank, there is water and the height of water column is 1.5 centimeter. The height of gasoline and air, that is not known, and I think this is what has to be found out. And they have also given us the specific weight of gasoline, that is density into acceleration due to gravity, and specific weight of air. So specific weight of water is not given, so we will treat the water density to be 1000 kg per meter cube. Okay. So let's see what the question means and how to solve it. Okay. So basically what they say is, they say that let us suppose there is some car or there is some bike, like a car like Swift Desire, and there is obviously a petrol tank in it. Okay. So in order to check, so I think your odometer, it tells you, the fuel gauge on the display, it tells you that whether the gas is full, whether the tank is full, half empty or fully empty or in reserve, right? So how it operates? Basically what happens is that there is a pressure gauge at the bottom. There is a pressure gauge at the bottom. Now suppose the tank is totally full. So when the tank is totally full, you will have petrol up to this much level. So inside the tank, there will be 25 centimeter of petrol and its upper surface will be exposed to atmosphere. Okay. So what will be the pressure at the bottom? Yes, very good. It will be atmospheric pressure plus 25 centimeters of gasoline, right? At a point, hydrostatic law says that at a point, the pressure is simply the pressure at top surface of the fluid. The pressure is the gauge pressure, and generally all the pressure measures, they give you 1.5 centimeter. Then above water, there is gasoline. We do not know the height of gasoline column. So let us call it as H. Centimeters, H in centimeters, and then there will be air column also. Okay. So now what they're saying is that the fuel meter is still showing full, but I think the fuel meter works on the reading obtained by pressure gauge, and the pressure gauge will say that whenever the pressure here is equivalent to 25 centimeter of gasoline, then only it is full, right? So basically what it means is that currently in this situation also, here the pressure is equal to 25 centimeter of gasoline.